What is going on, guys? Welcome back to a new video. Today we're going to be talking about heaps. Now, before I get into this, if you're looking for either a job or an internship, check out the first link in the description. I think you'll find it really useful. With that being said, if you're also enjoying the channel, please make sure to subscribe and also like the video. Kind of helps me out here. I really appreciate that. Now, to get into it, the heaps. Heaps are used to maintain a maximum or minimum value in a data set. So our example use numbers, since this is a straightforward value, but heaps have many practical applications. Imagine you're a demanding boss. Hopefully this is theoretical, but you always want the most important thing done first, of course. Once you finish the most important task, another one takes its place. Now, let's look at this heap real quick. This is a minimum heap. Now, how do you know this is a minimum heap? Well, because the number at the root, or like at the very top, is going to be the smallest. And then everything else down should either be greater than or equal to this, okay? So everything should be greater, yep. And then everything here should be greater or equal to, yeah. So this one's greater, that's good. This one is equal to, that's fine. And same thing for here. Now, if you had let's say you had 15 here, that wouldn't work because 10 is smaller than 15. All right. And you can manage this problem with a priority queue to ensure they're always working at the most pressing assignments, and heaps are commonly used to create a priority queue. Heaps tracking the maximum or the minimum value are max heaps or min heaps. We'll focus on min heaps for now, but the concept for the max heap is completely identical. Think of a min heap as a binary tree with two qualities. The root is always the minimum value of the data set, and every child's value is either greater than or equal to its parent. These two properties are the defining characteristics of a min heap. By maintaining these two properties, we can effectively retrieve and update the minimum value. Now, heap representations. So we can picture a minimum heap as a binary tree where each node has at most two children. As we add elements to the heap, they're added from left to right until we fill the entire level. At the top, we fill the level containing 12 and 20. The next addition will be uh, the left child of 12, starting a new level as the tree. We'd continue filling the level from left to right until 20 has its right child filled. Conceptually, the tree representation is beneficial for understanding. Practically, we implement heaps in a sequential data structure like an array or list for efficiency. Notice how filling the tree from left to right, we're leaving no gaps in the tree at all. The location of each child is derives from the formula. So the left child is the index times 2 plus 1. The right child is the index times 2 plus 2. And to get the parent, it's index minus 1 divided by 2. You cannot use this on the root. So let's say you had this one, okay? You're trying to find the child of, let's say, you're trying to find right? The 14, okay? It's the left child of 12. So to find the left child, you do the index times 2. So that's going to be, I don't know why they did it like this. There's a better formula to represent this. I believe it's just I times 2, pretty sure. And you can get it that way. It's I times 2 to get the left child, and then I times 2 plus 1 to get the right child. And then I divided by 2 to get the parent. But you have to take the floor function of that. But these formulas, I believe, should also work. So let's say we were to find 12 here. So you would do 1 times 2 plus 3. So, yeah, so 2 times 1 plus 1 equals 3. So this is 1, 2, 3. That should how it works. Yeah, that should be how it works. That's how you find the. You know what? These formulas I don't think are right. Yeah, I don't think these formulas are particularly right. Or maybe I'm doing it wrong. Let me know, but these are definitely not the right formulas. It's I times 2 for the left child, it's I times 2 plus 1 for the right child, and then it's I divided by 2 floor function for the whole thing, uh, and that's how you get the parent. So keep a lookout for that. Adding an element, so heapify up. Now, sometimes we'll add an element to the heap that violates the heap essential properties. We're adding 3 as a left child of 11, which violates the min heap property that the children must be larger or equal to its parents. So we need to restore the fundamental heap properties. This restoration is called as heapify or heapifying. Now we're adding an element to the bottom of the tree and moving it upwards, so it's heapifying up. As long as we've violated the heap properties, we'll swap the offending child with its parent until we restore the properties or until there's no parent left. If there's no parent left, the element becomes the root of the tree. So first, wait for this to go through. Okay, so 3 swaps with 11, right? But there's still work to do. And then 3 swaps with 5, and now it's restored. Now you see it's at the right place, right? And yeah, that's basically how you heapify up. Basically, you're taking, if it's smaller, you're moving it up. If it's larger, you'll move it down, right? For a min heap, of course. Okay, removing an element, heapify down. So maintaining a minimum element is no good if we can never retrieve it. So let's explore how to remove the new root node. In the diagram, you can see the removing of the top element could be messy. There would be 2 children orphaned. Instead, we swap the node 2 with the bottom rightmost child 20. The bottom rightmost child is simple to move because it has no children and it's the last element that you added in the heap tree. So unfortunately, we violated the heap property. 20 is the root node. We'll heapify down. Okay, now I want you guys to question this, okay? Why does 20 not move here, right? Why does it not move here? Because if you move it here, right? If you move it here, um, that will make it so. Okay, so if you move it here, 5 would go to the top, right? 5 would go to the top. Oh, okay. If you move this 20 that was here, if you move it here, then 10 would be the new root, right? But but you see 5 is smaller than 10, so you have to go this route with the 20, right? Once the 20 is up here, you have to go here. Since 5 is the smallest element, you have to put that in the root, and then you heapify down to the correct spot. So basically, to know where, if you go left or right, you have to understand, you have to go with the smallest element, since uh, it is going to be a min heap, right? Okay, so now let's take the quiz here and understand more about heaps. So heaps are often visualized as binary trees and implemented using a sequential data structure like an array. Yeah, That's true. They are a binary tree. In a max heap, what happens to the during the process of heapifying down? Okay, so max heap is where you have like let's say 100 and then 90, 80, 70, 60, right? It's getting smaller and smaller as you go down the tree. So heapifying down basically means okay, when there's a child of an element and the parent is greater, the element swaps its location. When there is a parent for an element and the parent is greater. Nope, that's not what heapifying down means. Okay. While there is a parent and the for an element and the parent is lesser. Nope. Okay, when there's a child for an element and the child is lesser, the element swaps location with the child. The child is lesser. No. So if the child is greater, then it'll swap. Because if you have a parent which is 100 and the node and the left child is let's say 70, okay, you want to switch with that so that 70, no, I'm sorry, it's the other way around. If you have a root node which has 70 and you have a left child which is 100, you would want to switch those so that the 100 goes to the root because it's the highest value. What element is removed from a heap? It's always the root node or the first element in the array. Yep, it's always the root node. In a min heap, what happens during the process of heapifying up? Now, in a min heap, basically when there is a, let's see, okay, when there is a child of an element and the child is lesser. Yeah, I think that's the answer, no? When there's a parent and the parent is greater. Oh, so these are, yeah, okay, that's heapifying down. Okay, so that's heapifying up. Okay. Just got confused with the terminology, but okay, when removing the maximum or when removing the maximum or minimum element from a heap, what element first replaces the root before heapifying down? The element at the bottom right of the tree or the last element in the array, the element with the mean value, the element with the greatest value, the element. Okay, yeah, it's going to be the element at the bottom right of the tree, or it's the last element in the array if you're using that, right? A heap is an effective solution for what kind of problem? When you need to create a relation between data in your data set, when you need to efficiently maintain a maximum or minimum value in a data set, when you need to keep a mapping of string values pointing to other values, when you need to maintain an ordering of what elements enter the data set. I think it's to maintain the maximum or minimum value. In a meme heap, what is true of the first element in the array or the root node? It is always the minimum value. That's pretty easy, right? Okay. In a max heap, what are the two qualities does the heap ensure? The root the root element is an even number? No, that's not true. The root or the first element is the largest value, yes. And every child is lesser than its parent. Yep, that's the right answer. And we passed with an 87. So yeah, hopefully you guys enjoyed that. Pretty good questions there. Like I would rewatch it if you want to learn more about heaps, but ultimately heaps summed up our binary trees. You can have a min heap or a max heap. If you have a min heap, the root is the smallest and it gets bigger as you go down the tree. A max heap is the root is the biggest and it gets smaller as you go down the tree. Now that's gonna end it right here. Thank you so much for watching and subscribe and like if you liked it, and I'll see you in the next one. Have a fantastic